This is a revision video for P5a Satellites and their uses. A satellite is an object that orbits a larger object in space. The Moon is a natural satellite of the Earth. However, there are thousands of man-made artificial satellites that are in orbit around the Earth as well. It's not just the Moon and our man-made satellites that are classed as satellites. The planets can be classed as satellites around the Sun as well. The Earth has got over 20,000 man-made satellites in orbit. Now some of them are really small, just a few metres across, but others can be very large military or commercial satellites, maybe the size of a bus. These satellites have got a variety of different uses. They can be used for telecommunications, weather prediction, military uses, satellite navigation or your GPS, scientific research and producing images of the Earth. This is the International Space Station. It's an example of a larger artificial satellite. If you look up at the night sky, you can sometimes see it passing through overhead. Its main use is for scientific research, but why does it stay in orbit around the Earth? The reason the satellites stay in orbit around the Earth is because of gravity. The gravitational attraction force is called weight. You can work out the weight of an object by doing the mass in kilograms times the gravitational field strength, which is measured in newtons per kilogram. Without the gravitational attraction force between satellites and the Earth, the satellites would fly off into space. The gravitational field strength varies on different planets because their masses are different. Generally, the larger the mass of the planet, the larger its gravity. Now, it's important not to confuse mass and weight. Your mass will never change wherever you go. Your mass is the amount of stuff you are made up of, or the amount of particles that make up your body. That is the same if you are on Mercury compared to if you are on the Earth, on the Moon, or on Mars. However, your weight will change. If you think about the equation we've just seen, the weight equals mass times the gravitational field strength, then if the mass stays the same and gravity goes up, then therefore your weight will go up as well. Now what I'd like you to do is have a look at the satellites in the table down here and have a look at their corresponding gravitational field strength. I would then like you to find out the weight of the Mars rover buggy on Earth, on Mars and on Jupiter. You might want to pause the video for a minute to work this out. Okay, did you work it out? If we're looking at these planets, the one that has the greatest weight will be Jupiter. Your weight equals its mass, which is 170, times 24.8. It has the highest weight for all of these planets, and that's due to its massive gravitational field strength. As well as the gravitational force varying on the mass of the two objects, it also depends on the distance between the two objects. If the two objects are close together, then the gravitational force of attraction between them is stronger. If the objects are further apart, the force is weaker. The gravitational force of attraction varies with the distance between the two objects. It varies in proportion to an inverse square law. This is the inverse square law that it follows. Now what it means is that the gravitational force of attraction is proportional to 1 divided by the distance between the objects squared. So I look here. I've got my two objects, object 1 and object 2. Now they are a certain distance apart from each other. Now I'm going to make that r equal to 1. If I then move object 2 out to here, then I have doubled the distance away from object 1. So then I'm going to make that equal to 2. Okay, so I've gone 2 times the distance from object number 1. Now if I look at that equation, I've got f is proportional to 1 divided by r squared. So if my r is now 2 times as big as it was, that means I've got 1 over 2 squared, or 1 over 4. So what that actually tells you is, if your r has doubled, while being times by 2, the gravitational force is now 1/4 of that which it would be if our distance was only 1. Now on a massive scale, so between the planets, this obviously creates a big difference in the amount of gravitational force. However, if we look at a smaller scale, if we look at the surface of the Earth, we can see that it's not all flat. It has bumps which are representing the mountains. Okay? Now it's important to understand that the gravity, its point of origin, is the centre of the Earth. So that means the distance to the top of a mountain is greater than the distance from the centre to the flat surface. That means that gravity on Earth can actually vary by about 1%. Now we mentioned that the Moon is a natural satellite of the Earth and that man-made satellites are up there, so we've got thousands of artificial satellites. We mentioned that planets are also satellites because they orbit around the Sun. Another thing that is a satellite is a comet, and the example there in the diagram is Halley's Comet. Comets, however, are a little bit different because they have very elliptical orbits. That means that at some points they are much closer to the Sun than they are at others. Now, when the comet comes in close to the Sun, it will move a lot faster than it does when it's out here. Now that's because the gravitational force of attraction is much stronger when it is closer to the Sun. Okay? And we can relate that to planets as well. So planets that are closer to the Sun, so Mercury, Venus, Earth, Mars, they have a shorter time period than the planets that are further out. So what that means is the ones that are closer to the Sun will move faster, and their time period, or the time it takes them to do one orbit, is a lot shorter than if they were further away from the Sun. So we're in that weaker gravitational field strength. Now Halley's Comet takes about 75 years to orbit. Mercury, however, because it's really close to the Sun, it only takes it 116 Earth days to orbit. And Jupiter, because it's further away from the Sun, takes 11.9 Earth years to complete one orbit of the Sun. Okay, now what I want you to do is pause this video and I want you to work through these graded questions. They go all the way from a grade D to a grade A star. Right, so I mentioned before that the planets that are closer to the Sun will have a shorter time period because they are experiencing a greater gravitational force of attraction. Now the same can be said for satellites. If they are closer to the Earth's surface, then they experience a greater force of gravity, so they will move faster and therefore they will have a shorter time period. If satellites are higher above the Earth, then they experience a lower gravitational attraction and they have a longer time period. So the example is there, the International Space Station, the ISS, is 340 kilometres above the Earth. It takes it 90 minutes for one orbit. Okay, now the satellites we use for television and telecommunications are higher up. They are 36,000 kilometres above the Earth. they take 24 hours to complete one orbit of the Earth. Okay, so we can see in this diagram here that this satellite is a greater distance from the Earth, so the gravitational force of attraction is smaller, so it takes longer to complete its orbit around the Earth. Okay? Now what we're going to start talking about is the motion of satellites. Now satellites are constantly moving in a circle, so their direction is always changing. So we can see here, this satellite, when it is at point A, it is moving along that trajectory. However, because the Earth's gravity is pulling it in, its actual motion is in a circle. When it gets to point B, it's moving in that direction. When it gets over here, the point C, it will be moving in that direction. Now the satellite is moving at a constant speed. Okay, so its speed is staying the same. However, its direction is changing. You should know that speed with direction is called velocity. Okay, so the speed's the same, but the velocity is always changing because the direction is always changing. So the direction relates to our velocity. Because the direction changes, the velocity changes. And if you have a change in velocity, so say you are going from 10 meters per second to 20 meters per second, so you change your velocity. In my example, you got faster. So that means you have accelerated. Okay, so in that way, the satellite can be constantly accelerating and also have a constant speed. Now there are two main types of orbit for artificial satellites. There are satellites that are in a polar orbit and satellites that are in a geostationary orbit. The satellites that are in a polar orbit go around the poles of the Earth. Now they are normally in quite a low orbit, and because they're in a low orbit, they have a short time period. They are travelling quite fast. The second orbit is a geostationary orbit, so that's this one here. It is further out. It has a higher orbit. Its time period is equal to 24 hours. So it looks like, to you, if you were stood here on Earth, it looks like the satellite will always be above you. So as the Earth rotates, the satellite rotates at the same time, so it will always look like it is above you. Okay, it's wrong to say that it is not moving, because it is moving, but it is moving at the same speed as the Earth. One orbit is completed in 24 hours. Okay, now satellites are moving in a circle. We saw that before. Because they're moving in a circle, they are constantly accelerating, and also because they're moving in a circle, they need a centripetal force to keep them going round. Now this is provided by gravity. If there was no centripetal force, then the satellite would fly off, so it wouldn't be kept within its orbit. Okay, so the type of orbit that a satellite has determines what job it will do. Now, some polar orbit satellites can fly extremely close to the Earth and can have a time period of about 2 hours. So they can sweep out the entire surface of the Earth in a very short period of time. These satellites are really useful for weather forecasting, so looking at the weather patterns in the atmosphere, for imaging the Earth, so mapping, and also for military uses such as spying on other countries. Okay, so as I said before, geostationary satellites are higher above the Earth's surface, So they have a longer time period because they are travelling slower, because they are further away from the gravitational force, and they orbit every 24 hours. So they're looking like they're staying in a fixed place above the surface. These satellites are very useful for communications. They can also be used for TV and radio signals and local weather forecasting because they're keeping their eye on one particular area of the Earth. They're also very good for relaying signals from one satellite to another. So if we are here, we can send our signal to this geostationary satellite. We can then send it to this one. Then we can bounce it around to this one and then down to here. So it allows us to keep in communication with people that are at the other side of the Earth. Okay, so this is the hard part. More on satellite orbits. The centripetal force acting on an artificial satellite is always at right angles to its motion. So if its motion is this way, the gravitational force, the centripetal force, is that way. So it's always directed towards the centre of the Earth. As the direction of the satellite is continually changing, its velocity is also changing. So it's accelerating. So as we said before, as the satellite's moving around here, its direction is always changing. Its speed can be constant, but because its direction's changed, its velocity's changed. Okay, the satellite is always continually accelerating towards the Earth. Now, because of that, it is always being pulled towards the Earth. It's able to stay in orbit because of its motion, how it's moving so fast. So at point A, the satellite's velocity is at right angles to the acceleration and the centripetal force. The force causes the satellite to change direction, but it stays at the same height. This happens at all points in the orbit, and that's what leads to the circular path. The satellite's high velocity keeps it in a stable orbit. If it were to stop, then it would accelerate towards the Earth, so it would pull towards Earth. The distance between the Earth and the artificial satellites in lower orbits is smaller, so the gravitational attraction is greater. This means they travel fast. Okay, the satellites that are in low polar orbit have a much shorter time period because the gravitational force on them is larger. So they travel much faster than those that are in a geostationary orbit. So the key points to remember here is that there is a centripetal force acting on the satellite, which is always at right angles to its motion. This is provided by gravity. The satellite's moving at a constant speed, but its velocity is changing because its direction is changing. Therefore, it's accelerating. It is kept in its orbit. It doesn't fly off or it doesn't crash into Earth because it's travelling so fast. You need to remember that satellites nearer to the surface have got a greater force acting on them, so they move faster. So if we think back to the gravitational force of attraction, it's proportional to 1 over r squared. If we make r bigger, so if we make our distance bigger, then we make our force smaller. So the further away you go from your massive body that's creating that gravity, then the less force of gravitational attraction you will feel. Okay, so that's it for satellites and their orbits. What I'd like you to do now is stop the video and have a go at this extended writing question. So this will be one that will be worth 6 marks in your exam.